Hello, everyone, and thank you for joining us today. My name is Erin Majerowitz, and I will be your host for this NASA Technology Transfer Program webinar on NASA's Serial Arrayed Waveguide Grating. Our presenters today are Dr. Mark Steffen and Dr. Fabrizio Gambini. Dr. Mark Steffen received a BS in physics from the University of Delaware in 1992 and an MS and PhD in applied physics from the University of Maryland, Baltimore County in 2003 and 2008, respectively. He has worked at NASA's Goddard Space Flight Center since 1991, developing laser and electro-optics technologies for space-based applications. Dr. Steffen worked on several satellite programs, including leading the laser development for the Advanced Technology Laser Altimeter System ATLAS, which is currently flying aboard ISAT-2. His research activities include lasers, optics, laser instruments, and integrated photonics. Dr. Fabrizio Gambini received his BS and MS degrees in telecommunication engineering from Politecnico di Milano in 2010 and 2012, respectively, and the PhD degree in 2016 from Scuola Superiore Santa Anna, where his main activities were the study, design, and characterization of photonic integrated devices based on silicon, on insulator, and indium phosphide technology platforms for datacom and telecommunication applications. Dr. Gambini was also with the National Inter-University Consortium for Telecommunications as a research assistant within the European project IRIS, developing a high-capacity and reconfigurable wavelength division multiplexing photonic switch based on ring resonators. In 2018, he joined the Integrated Photonics Laboratory at University of California, Santa Barbara as a postdoctoral research associate working on the design, fabrication, and characterization of photonic integrated devices for data center interconnects, free space communications, and remote sensing for Earth science applications. In 2021, he joined the University of Maryland, Baltimore County, and the CREST-2 program with NASA's Goddard Space Flight Center in Greenbelt, Maryland, as an assistant research engineer. He's developing photonic integrated circuits for hyperspectral remote sensing and LiDAR applications. Following this webinar, Josh Levine from NASA Goddard Strategic Partnerships Office will be giving a short presentation on how to license NASA technology. Before we get started, I'd like to point out that your microphones will be muted throughout this presentation. So if you have any questions, please type them in the chat box in the lower right-hand corner of your screen, and we will answer them during the Q&A session at the end. So at this point, I'm going to turn it over to our presenters.
Thank you for the introduction. I'm Fabrizio Gambini, the presenter of this work. The inventors are Dr. Mark Steffen, Dr. Hernan Moreira, and me. So this is the summary of our presentation. I will start with a brief introduction about the background and the state of the art of the technology. Then I will we will show you the proposed device, in particular focusing on the advantages and the improvements, the experimental results. We will also show the new generation of devices that are under development at the moment with the expected performance, and in the end, the conclusions. So optical multi-channel narrowband optical filter play a very important role in different scenarios, in particular high-speed optical transmission system and microwave photonics. In the ideal world, this filter have a rectangular shape, so they don't add any distortion because of their flat top response. They have an infinite out-of-band rejection. They don't introduce loss. They should provide tunable multiple channels and everything in the smallest and light and passive packaging. Of course, reality is not is not like this. So different solutions have been proposing during the years, in particular to provide flat top spectral response. Here I reported some examples. So you can obtain actually transparent optical filter with the liquid crystal on silicon or using free space bulk components, and they actually provide flat top response and good rejection. The problem is that they just work for bandwidth that are about 10 gigahertz and beyond. After narrower filter with this kind of technology, they mostly have a Gaussian shape, and also it's hard to provide a high number of channels. Moreover, they use commercial off-the-shelf parts, so they are not really integrated solutions. So other technology are based on fiber brick gratings and the multi-layer Fabry-Perot ethanons. They also offer flat top response and also multi and narrow bandwidth channel filters. So in particular, with this solution, you can lower the bandwidth, but for instance, the normal FBGs, they show high loss and they are hard to tune. And here I report an example of a work that from 2017. This group proposed a phased sample FBG, which it really improved the loss and the bandwidth, and they showed results below 1 gigahertz of bandwidth. But the fabrication constraints, in this case, they limited the channel separation. So this solution can be useful for narrow bandwidth filter with flat top response, but the tunability and the channel separation have strong limitations. Another solution, in particular photonic integrated solution, are based on microring resonators, and they can provide a tunable and compact passband filter. In particular, when they are designing cascade or in series configuration, they can offer also narrow band and flat top responses with high rejection. So for each channel, there are multiple ring resonators, at least 2, and all of these resonators need to be tuned. Moreover, in the series configuration, you need also to properly control the phase delay between these rings in order to maximize the performance. We have also to say that the narrow bandwidth filters require low splitting ratios. So this could, let's say, lower the power at the output of the filter. Moreover, this ring resonator, when are designed for a high finesse configuration, they become quite sensitive to temperature variations. So here I reported some simulation that we perform for 10-channel filters based on 2-ring configuration filter and 3-ring configuration filters for each channel, which means that to have 10 channels, in this case at 4 gigahertz, we require up to 40 and 70 electrical control, respectively. As you can see, this system they provide actually flat top response, and they also offer very compact solution. However, they provide low output power for narrow bandwidth, and the system, because of the high number of controls, the scalability of the system is challenging. Other solutions are based on arrayed waveguide grating, which are planar devices that are used for multiplexing and demultiplexing components in WDM system. So in this configuration, it's called parallel AWG, and it's composed of a 2-star coupler and an array of waveguides. So the first star coupler divides the input power equally all along the different at the input of the different waveguides, And the different waveguides actually add a phase delay that, of course, needs to be engineered during the design phase. And the second star coupler just acts as a recombiner, and it provides also multiple output channels. So here I reported the transfer function simulation, and the spectral response of this filter depends on the order of the grating and, of course, the parameter of this grating. So the number of grating elements, in this case, waveguide, the group index, and also, as I said, the length of the different waveguides. So the phase delay added by each waveguide. So as I said before, you need to optimize the optical path of the different waveguides in order to optimize the filter response. This solution doesn't provide a flat top filter, but it provides an integrated solution, so there are no cuts or moving parts. It provides multiple channels, but not, as I said, flat response. Moreover, when we try to let's say, to build a narrow bandwidth and channel separation filter, the fabrication inaccuracy, they can become a big problem because they can jeopardize the filter response. And this kind of design, this kind of component doesn't allow an easy access to the waveguide. So it's not easy to, let's say, try to compensate the fabrication inaccuracies. So here I just put this table in order to summarize the different components that I just showed. As you can see, I don't want to repeat, but as you can see, there is not a magical solution for every scenario. So we need to choose a different component or different technologies for the different systems or scenarios. So our proposed device is actually called serial AWG, and is based on one long delay line, and we have different directional couplers that basically split or take part of the input signal in the delay line, and then they route all the signal at the single star coupler, which perform the Fourier transform of its input distribution. So the spectral filter response is basically the Fourier transform of the intensity distribution at the input of the star coupler. For the ones that are not familiar with the Fourier transform, it's just a mathematical operation that allows to transform a signal or a function in domain X to another function in the domain Y. And I reported here the formula in the center. I don't know if you can see my pointer, but and on the left I reported also some examples. So the Fourier transform of a sinusoidal function is a single tone. For a Gaussian function, it remains Gaussian, and is basically the shape that we found in the parallel AWG filter, optical filter. And if we have, for a sinc function, we have actually a rectangular function. So in our serial AWG, we want a flat top shape. So we want a rectangular function at the output of the filter. So in one way, we can control the phase and intensity distribution at the input of the star coupler in order to provide a sinc function. And another thing that we can do is that we can also decide we can also, let's say, do the opposite. So from the filter shape that we want, we can reorganize the directional couplers and the splitters in order to change the intensity, and the waveguide to change the phase distribution in order to have that particular filter shape at the output. So our solution provides access to, as I said, directional coupler, and this allows us to have a rectangular or other filter shape. it allows to it enables the access to the number of the delays and delay length. We can scale much easier the design, and this is important to achieve sub-gigahertz bandwidth filter with very narrow channel separations with high rejection. We can also control the different delays. So we can tune each single waveguide, and this is very important to compensate the fabrication inaccuracies. And also, this provided tunable channels. And also another important point is that this design is viable for an integrated solution. So we can really minimize the size, the weight, the power consumption, and the cost of each component. So, for example, let's assume that we can change the directional coupler, so the splitting ratio. Here I reported three different scenarios. So in the first in the first row, you can see three different scenarios of three different configuration, intensity configuration at the input of the star coupler due to the different splitting ratios that we have on the directional coupler. In the first case, we have a constant input distribution, and in the second case, we have a kind of, let's say, bell distribution. The third case is a sinc function, and as you can see, this in the second line, the shape of the filter changes. So we can pass from Gaussian to kind of more Lorentzian, and in the third example, more flat top response. So our solution can provide multiple channel filter with flat top, so rectangular spectral shape. We can, as I said, we can also have an easier access or control on the number of the delays that we can put in the system, in the filter. And here I reported three examples with 18, 33, and 67 different delays, and we can swing from in these examples. Of course, we can swing from 5 to 0.9 gigahertz, but we can go also lower, of course. And what is worth noting is that the free spectral range is the same, is about 40 gigahertz in all the three examples. So if we increase the number of the delays, we can narrow down the bandwidth, but we can also improve the finesse and the channel rejection, as you can see from the different plots. If we consider the last example, we have less than 70 electrical controls, and we can achieve a sub-gigahertz flat top channel response. If you remember, when I was talking about the multi-ring resonators, we had the configuration with 3-ring resonators was, let's say, was good, but provided 70 electrical controls. So I'm putting this example as a reference. Another advantage is that our device can also support longer delay lines. So this is also good, also in this case, to narrow the filter bandwidth and the channel separation. And here I reported three different examples from our simulation, from 1,000 micron delay step and 14,000 micron delay step. Again, as you can see, we can change the bandwidth from about 10 gigahertz to 0.9 gigahertz. Again, we can go below, but changing the step of the delay line, so it also changed the free spectral range. So longer delay, in our case, we need to consider that longer delay lines, it reduces the bandwidth, but the finesse stays constant, and also the channel rejection. But we can accept the longer delay line compared to the parallel AWG component, and so it's an easier access to sub-gigahertz flat top response filters. And here I reported, let's say, a full example of our system. In this case, we configure the directional coupler, so the splitting ratios value, Ki, in order to have a sync function, as you can see at the bottom right. And this allowed us to have a flat top response for all the 16 channels filter. With in this case, the bandwidth was 4 gigahertz, and also the channel separation was 4 gigahertz. But we were also able to achieve about 20 dB of secondary lobe suppression. So this is actually our first full prototype that we developed in silicon nitride platform. We choose this platform because it provides ultra low optical loss, low power consumption, and minimum size, weight, and power consumption and cost. But I have to say that the design fits also with other photonic integrated platforms, such as silicon on insulator. This is the design of the first full prototype, as I said. On the left, we have the input waveguide. Let me see if I can. There's a pointer. So on the left side, we have the input waveguide. The red lines here are the, let's say, the optical delays path, and the blue lines are the optical waveguide, and the red lines are the heaters above these waveguides. And the green contacts and lines that you can see here are the metal routing for the heaters for the contact. At the output, we have the star coupler and 10 optical waveguides. So we had 17 thermoelectrical controls in order to compensate the fabrication inaccuracies on the delay lines. And here I reported a picture of the actual device. Again, the bright parts are mostly due to the metals, and you can see these blue features that are the optical waveguide. But just to give you some number, this circuit footprint is about 20 millimeter times 4 millimeter, and it has an optical loss of 0.2 dB per centimeter, thanks to the silicon nitride platform. We developed this device in order to achieve a 4 gigahertz bandwidth and 4 gigahertz channel separation, but in this case, we didn't have a flat top response. And here I want to show you some experimental results. So this is the IB curve of one of the heaters that we were using. So the result, the red line is the measurement result. The blue line is the console or FEM simulation result. As you can see, there is a good match. So we can let's say predict with high accuracy the thermoelectrical performance of the circuit, not only the optical performance of our filter. And here I want to show you the effect of the fabrication inaccuracies. In particular, I'm focusing on only one channel of the filter, but if you see the pink line, the shape of the filter was let's say kind of destroyed by the fabrication inaccuracies. So when we tuned the single delays, we were able to obtain the red curve, which is way more similar to the blue curve that is related to is the result of our model. We were able to achieve 4.1 gigahertz of bandwidth and a side lobe suppression of about 13-15 dB. So what I'm showing here is that our solution can really compensate the fabrication accuracy. We can go with the narrow bandwidth. I want also to notice that during the experiments, we were limited by the testing component that we were using. So actually this performance will be better. The performance that I'm showing now will be better in the future, in the sense that they are already better. We were just limited in the control of the filter. And here I want to show that we were also able to achieve our target of about 4 gigahertz channel separation. Again, in this case too, we were limited by the testing component, but we met our goal. And this is the summary of the achieved component, and the comparison with our expected goals. So the channel separation and the bandwidth goals were accomplished. We were able to tune the filters and also compensate the fabrication inaccuracy, and we validated our model thanks to this generation. After this, we didn't stop. We started to design a new generation of components, of filters. In particular, in this new generation, we improved the thermoelectrical efficiency of the heaters, so we can really minimize the electrical power consumption. We also improved the design of the directional couplers, and we added tunable directional couplers in order to change the intensity distribution at the input of the star coupler. And in this case, we use a shorter coupling length because they are more robust to the directional coupler can be more robust to the fabrication inaccuracies. This on the left here, you can see our new design. Again, the blue lines are the optical waveguides. The red parts are the metal heaters on the top of the waveguides, and the green lines are the metal routing for the electrical contact. So our new generation that is currently under fabrication in this moment is composed of 33 tunable directional coupler and 33 delay lines, which can be electrical controlled. What I want to point out is that we don't need to use all of these controls. It just depends on the quality of the fabrication. So if we don't have fabrication inaccuracies, actually we don't need to apply any electrical signal. Of course, because of the technology, there will be some fabrication inaccuracies. So we decided to, let's say, have the maximum flexibility in order to optimize the spectral performance of the filter. So the new delays, the heater on the new delays can maximize the thermal and electrical efficiency. They can also minimize the crosstalk. And this design was engineered in order to ease the packaging of the photonic integrated circuit. Our goal is, again, to achieve a 4 gigahertz bandwidth and channel separation. In this case, we want also to achieve a flat filter response with 20 dB, at least 20 dB of filter rejection. This is the spectrum, the simulated spectrum of the design of the device that I just showed. As you can see, we have we expect a flat top response with 20 dB of side loss suppression, 4 gigahertz channel separation, and 4 gigahertz bandwidth, around 1550 nanometer. And we designed the device in order to have 1 input and 10 optical output. So going back to the performance summary and the comparison with the state of the art, I added in the last line our components so that you can have a reference. So our solution is an integrated solution, and as other can provide a flat top response, it can also achieve narrow band optical channels, and can provide different multiple optical channels with high rejection, and the filter is actually tunable. Of course, we will require electrical controls, and the number of the electrical controls that will be actually active will depend on the on the quality of the fabrication of the photonic integrated circuit. So in conclusion, our serial AWG concept enables a broad range coverage, high resolution, narrow bandwidth channels, which is difficult to achieve with the classical AWG design, the parallel one. The shape of the filter can be changed, varying the splitting ratios of the directional coupler. Our proposed solution can be easily manufactured and packaged on for different photonic platforms, so that we can minimize the SWaP-C. And of course, this innovation can be applied at different systems that require high performance and optical filtering. For the moment, we demonstrated 4 GHz channel bandwidth and separation because of the requirements of our project that we're working on. But the design easily enables narrower bandwidth and channel separation below 1 GHz. This is the end of my presentation. Thank you.